As I said, this is a broad introduction to what we can do with machine learning in the language. I'm going to show you several areas, and they will be divided mainly for learning paradigms. And then I'm going to define what supervised machine learning is, unsupervised machine learning, what are the problems and what are the solutions. And after a brief introduction, we are going to look at how to solve these problems in the Wolfram language in like a broad view. And then we are going to look at some built-in functions that were built using the machine learning functionality. And after that, we go in depth on each method. Okay, so what do we mean by machine learning? Well, just by looking at the literal of words is like we are teaching something to a computer, and so the idea here is that when we write a program, for example, we tell everything to the machine about what to do. Like if there is this, do that, or like stop, or like switch, or like do a for loop. Like with machine learning, it's also like normal programming, but you leave 3 parameters, and these 3 parameters are meant to be filled in by the data. So the core concept here is that we are writing a program that can accommodate knowledge from real world data, and this is very powerful. So here, for example, I show you like 2 things. Like one that you might not even consider machine learning, but you have probably done at school, is you can fit a polynomial, for example, through a list of points. And well, I mean, the typical school task is like you have 2 points and you find the best line, or the only line passing through those points. But you can also find a line passing through multiple points. So the idea is that in that case, you're going to try to, for example, write an error function, find how bad the line is going through the point, and try to make that error minimal. So this is a small machine learning program. You can have a very big machine learning program, like a neural network. So, for example, in this case, this example, like I put an image in, which is thousands, if not millions, of pixels. So those are all input data, and there's a complex thing that has been tuned with many examples, and at the end it will tell me, okay, I think this is an image of a cat. And so in this case, you can see like the true power of this is that if you build the structure well enough, you don't need to manually specify all the parameters. Like the old style machine learning was like, oh, I think that cat must have like 2 ears, so maybe I write a ear counting function, and it has, I don't know, these colors, so I will like kind of build another layer of classification by color. So like all these things were like kind of manually crafted, which in some cases works very well, but it doesn't scale really well typically. And so this is where like machine learning comes in. It helps you crafting just a simple pipeline and then filling in parameters by the data. So as we see, like typical tasks are those kind of like, the machine learning works best for those kind of like fuzzy tasks where I mean, the answer is not like 15, like 3 times 5. You wouldn't want to do that with machine learning. But given the probability of what's in an image, it doesn't matter if this image is 90% a cat or 91% a cat. The answer will still be cat. So that's fine. Or like in this example, we are taking like an age and a sex, and we are predicting the person's height. So in this case, there's not really right answer, because it's not that every female 6-year-old have the same height is a statistical answer. So like this kind of problem, we can analyze a lot of real world data and give kind of a prediction, like a distribution, I would say, distribution output. They are like very good problems for machine learning. It performs very well also predicting sort of probabilities of classes. Here is dog, cat, predicting probability of words in a sentence. So this is used now a lot for text translation. I think you might have used DeepL or Google Translate to translate some text. You can predict the continuation of a time series. You can detect anomalies. You can cluster data. You can teach a robot how to walk, or you can teach a computer program how to play games. This was from my ultimate, the famous Go match between AlphaGo and KG. Was like when AlphaGo won. So this was considered to be a very, very difficult day for a machine to learn. And with the kind of old-style programming, just try all the possibilities and writing rules, it was almost impossible to solve this problem. With machine learning, by analyzing a lot of games and kind of crafting a strategy and let the machine free to experiment and set its own parameters, in the end, it was possible. Okay, so I mentioned learning paradigms. What is this? What are those? Those are kind of broad classification. And I mean, true to the spirit of machine learning, they are mostly dependent on how the data is coming in. So when I speak of supervised learning, I refer to algorithms that are meant to be used when you have input data and output data. What does it mean? That you have labeled data. So to go back to the example before, we might have a collection of years and sex, and also the height of the person. So now my program would like to predict the height variable with the other two. So this goes supervised because I know the right answer, and I can check if the machine is performing correctly, and I can build some errors, and then basically fine tune everything. Supervised learning is a very, very common paradigm because a lot of like data now is coming this way, or it's also historically a lot of data sets were crafted this way. We have two main functions that we're going to check that performs the two main supervised tasks, which are classification, like I get an image and I want to say if it is dog or not, or prediction, which is also called regression. That means I have also a set of variables and I want to predict a value using those, like the height of a person or the probability of earning a certain amount of money if I pick a certain university. You can go wild with this. Unsupervised learning, on the other hand, deals with unlabeled data. That means that, for example, I only have a list of images, or only have a list of pairs of gender and height, so gender and age. So in this case, there's no answer in the data, and what I want to do with that data depends kind of on the application. So one basic thing is clustering. So I try to find like structure in the data, or I can try to kind of simplify the data. It's kind of an advanced structure searching, and I can want to kind of see if I can project my data in a simpler space. Like, I don't know, I have like a list of 10 variables, but maybe I can combine them in only 2 numbers, and that will still keep most of the information. Imagine something like principal component analysis. We have things like distribution learning or anomaly detection. Like, for example, we have a list of this sex and age, and we have like a person which is like much older than the others. So in that case, I want to be able to flag it and go and check what's wrong there. Missing value synthesis is also an important task. It's like I have one pair with 1 over 2 is missing, and I want to be able to fill it in based on the statistics. But we're going to see examples of this. Reinforcement learning is kind of a mixed paradigm where the model is typically called agent, and the answer of the model is an action. Like, imagine like a robot that needs to learn how to walk. So it will try to kind of move and then see if it is still standing up. So it needs a form of feedback. So there's no right, wrong answer. There's a feedback from an external environment. And then you typically have a reward. So, for example, I need to stay upright for a certain amount of time. or I need to reach the other side of the room. And so in this case, the program will try to maximize the reward. It's not an easy way to it's a kind of finicky way of programming. It's very powerful, but it's very tricky to get it right. So it's not largely used yet, but there's a lot of research on it. So data mining, this is okay, a bit complex to explain here. I'm just going to skip it and we directly look at examples here. So let's see here. What's kind of an overview of what we can do? I think that Britta already showed you some functions, possibly classify and predict. We have functions that are doing clustering. We have functions that are doing unsupervised data tasks like dimensionality reduction or feature extractions, like going from stuff like images, audio files to vectors. So as you can see here, these functions are all task-oriented. So in the name, they typically contain not the method that they are using, like a logistic regression or a decision tree, but they contain the task that you can use them for. And one thing that they have in common is that they are fully automated. And what I mean by fully automated is that you can use them directly, and you can throw almost any type of data at those. Like you can, if you like, you can throw images, you can throw text, vectors, and you can select a specific method if you know what you're doing, but you don't need to. And this also implies that you don't have to fine-tune the method yourself if you don't really know what's important. You can just let the functions like try and give you the best answer in the reasonable amount of time. Another completely like independent framework that we have is the neural networks framework. And this is basically a single method, neural networks, but it's very flexible and powerful. So it kind of deserves kind of some special care. And so here it's not like really task oriented. It's more like something like a toolbox that offers you the capability of building a model and train it yourself. I'm going to touch it. I'm not going to touch it here because it's kind of would deserve a talk on its own. But I mean, we have like a big tutorial in the documentation. Okay, let's start by some built-in functions, which is stuff that is using machine learning, and this has been already implemented by us kind of as a showcase or to kind of make it easier to directly use, like they have some applications instead of like starting from scratch every time. So okay, here this is a function classify. Here you would typically, in the first argument, you would typically put the training data, and you can also directly put the second argument optionally, that is you want to apply the classifier to something. So here I'm not putting the training data, I'm putting a string because this is kind of a pre-trained classifier. So if I press Shift Enter, so this one says English. So this thing here built, like actually called the pre-trained classifier and apply that to this string. And in this case, it will apply to this other string and say that's French. What happens if I don't put the second argument? Well, in this case, I just get a function out. This is called classifier function, and the advantage is that I can really apply it multiple times to different inputs. For example, here I have this Facebook topic classifier, which was trained on a bunch of posts in Facebook, and I apply to I play football, and I get sports. The point I was making before is that if you check the documentation, you see that classify can be used with a list of examples, like what I mentioned before, tagged, like labeled data, example and the class, example and the class. So here is another use case where I can just already, I'm kind of directly calling something that was trained before. So we did the training with something like this and saved it in the system. But you can, I mean, they're really indistinguishable. You can train something yourself on load the built-in. They will always create a classifier function and use it on the data. The advantage of these kind of pre-trained classifiers is that you don't need to have data yourself, and you can start immediately experimenting with this. So for example, here I'm taking this Facebook topic classifier, and I'm using a little front-end programming. Sure, I can make the text bigger. So I'm creating like a column with an input field and a column of the first three most probable topics. So if I evaluate this, it creates this interface, and I can say, for example, I would like to visit Rome, and goes, okay, this is 91% travel. Or I like to relax on Sundays. Okay, this is, you see, pretty low, but means a bit unsure. Maybe in the training set, people are not relaxing much. So this is a lesson also, like these functions are not magic. They will try to distill the knowledge that you pass them while you're training these models. So Sunday was raining. Okay, so this is the best class now is weather. This was one classifier taking text as input. We have built-in functions that have, I mean, they live in their own. They're an outside classifier predictor. They have their own specific functions because maybe they're a bit more complex, and you would like to set specific options. So, for example, here I can use a function image contents on this image, and this would create a data set where it tells me like this an image, a sub-image, it is a domestic cat, this was a bounding box, and this was a probability, and this was a dog. So this is also built we pre-trained a model and put it inside this function. You can use like different variants, typically this function, where you can, for example, map the concept of dog to some entity that we have in the system. So in this case, with dog is possible. So if you check this, this is our internal database representation of dog that knows about basically all the species property, and then you can now immediately use to do some other computations. So ask for the scientific name and ask for the typical body temperature of a dog. So we try to write function that kind of bridges the gaps between fields, if it is possible. So I was mentioning that these built-in functions are here also because you can directly build more powerful application. So for example, we don't have any image captioning function, but that's not too difficult to build. So I put some code here. If you want to look at it, you can uniconize it. And basically these things define a function that will run image cases with some threshold, then check like if we have any detection. So if we don't have any detection, we just say that we don't identify anything. And if we have something, we build a string that says what's inside. So in this case, it says an image with one dining table, 3 bowls, 1 cup, and 1 spoon. So I think it found this glass, these 3 plates, the dining table, and maybe didn't notice it really depends on the image. And there's another lecture. If you want a super high accuracy with this, you need to go very deep with the training. So for this kind of general purpose, is very difficult. This is why a company like Tesla or Uber are kind of using kind of spending millions and having a lot of people driving around collecting data, because if you want to be super sure, you have to train a lot. The good news is that for practical application, which is not self-driving cars, but more reasonable in scope, you can actually get very good results on precise application, which are like not like drive like a normal human being. So we saw 2 domains, text and images. We also have audio, for example. So you can ask like what's inside here. I don't think I shared audio, but there's a bird chirping here. So the closest thing in the training set was whistling. Whenever we can, we try to publish these models. So for example, the network that is in here in audio identify is published with this name in our net repository. I don't know if it was already shown to you. The net repository is this website where you can have a lot of pre-trained network that are doing a variety of tasks, and is a great starting point if you want to play with neural networks. And each one of them will have like a specific documentation page. Sorry, my internet is a bit slow. Where you can basically see how it works. So, for example, it's a segmentation network, and it basically gives you all the information you need to play with this. Other thing, text structure. So this is another typical machine learning task where you have a string and you want to kind of do grammar analysis on the content. So here's a piece of text that says things about the dodo, like is an extinct flightless bird. The relative was another extinct bird. Living relative is this pigeon, blah, 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 blah. And then you ask a question. So you say, how big was the dodo? And this network kind of tries to find the answer in the string. And in this case, is in this sentence, some fossil remains show the dodo was about 1 meter tall. So in this case, what machine learning is doing is kind of try to build a probability model for each substring to where the answer might be. In this case, it got it right. So we also this model is available. We have text content, text cases, which are similar, like a kind of mirror function to what we saw in the image case. So for example, here I can take the Wikipedia page for planets, at first 10,000 characters and say, find all things that are planet. I just give a type here, and this is kind of going through the string and finding what it thinks is planet. So in this case, for example, it picked the whole sentence. In most cases, just pick what we actually humans consider to be planets. Also, backends for these are in the neural network. You can use these models to build applications similar to what I did with the classifier function. So here, for example, I use generate sample and the GPT-2 function, neural network, to complete this sentence. So this will give me given one string, the full string will give the probability of the next token. So you see if I fold it, actually nest it in this 20 times. So it says Albert Einstein was, and it has space, so it's kind of gives reasonable things. And you can have fun with these change parameters of this network here, and find different like more or less crazy continuation for this. So this is definitely not safe for work. So I'm not going to evaluate too many of these, but some of them are funny. So I encourage you to try. Okay, so enough with built-in stuff. Let's have a look at how you can practically build your own models. And we start with supervised learning. So refreshing what this is a case where your data that you want to learn from comes with input-output pairs. So I have the right answer, and I have the variables that I want to use to find out what the answer is. The two typical classes, the class of tasks that we have, as I said before, are classification. Classification, you can imagine like that you have like kind of integer. you predict an integer value, like independent classes, like dog, cat, dodo. While regression, you are trying to predict a continuous variable. So this is an example where we use the function classify. We don't have any string now here. We have numbers and we have a string, which is a corresponding class. So as you can see here, like I wrote it in a way that with low numbers get classified as A and a kind of higher number as B, but I mean, this is just to create a very simple example. And so this is what I meant before by automation. So in this case, it's create a naive-based classifier. It picked the parameters, so you don't have to do these things yourself, but you can, of course, check the documentation. We have documentation for each method, so you can open the documentation and check if you have options here, how you can set them, and you have several examples. But you can also take advantage of the automation and just you already have like a functioning thing. So 1.5 is classified as A. Of course, you can like this is not really saying A. This is the model is predicting a bunch of probabilities, and in this case, the answer is A because the probability of A is higher than the probability of B. We have also functions to inspect these models. So if you throw this this classifier function to information, it will tell you a bunch of things. So this was taking in numerical data in input. The classes are A and B. The accuracy measure on the during the training was like 75%. This is done using cross-validation. So you kind of take out one point and try to train something with the others and predict. So this example set was very small. So 5 examples. So I wouldn't take any of these measures for the truth. But I mean, for serious problem, this is very useful. It's going to tell you the method that was picked and kind of speeds and some how big is a model and stuff like that. For prediction, basically it works the same way. Just instead of having a class on the other side of a rule, you have a number. So in this case, I'm just doing this and I'm building a predictor, and it works the same way. And I can again, this is not the answer of the predictor. The answer of the predictor was a normally distributed variable, and with a given mean and variance. And of course, the best answer given this distribution is a mean, which is 3.268. But you can also, plot the distribution and see that, for example, like given this is no, sorry, it's not distribution. This is the best answer given the input, and you see that this is a piecewise function, because in this case, the method that was selected is random forest, which is a bunch of binary classifier, is a bunch of trees that are saying yes, no, and I have some nice visual later, but this is not a smooth function. And this is another lesson. Like most of these functions are not continuous. This is typically not a problem because you don't I mean, as long as the prediction is statistically sound, you don't care much of the shape of the function. And when I say before that if you work on numerical data, you don't have to do anything, this is because you can work on non-numerical data. So for example, here my predictor takes in images and is trying to build a model, like given one image. Like for example, this I have this image and I say 40. This is the area of the pink region. So he's trying to predict a model given an image, tell me the area. So in this case, is using this predictor to tell me its best guess. So again, this is a quite small training set, but it's gonna do its best to give you the right answer. Okay, so let's see immediately one application. So we had the Facebook topic classifier. Can we build our own classifier? Well, let's see. So I'm going to do something simple here and just use 3 topics: physics, biology, and mathematics. And I'm using the function Wikipedia data to get the pages for these topics. So this is okay. It's done. Let's say let's take a look. String take of texts 1, and let's say the first 1,000 characters. This is basically, yeah, you see the intro of the Wikipedia page. And what I'm going to do with this is I'm basically saying like text is a vector of 3 long strings, and I'm saying like use these strings, and this is kind of an interleave, like transpose of a syntax before. I'm giving all the examples here and all the classes here. So I have three strings here, and the topics are physics, biology, and mathematics. So I'm running this classifier. So this is using a Markov model because it's the sequence of it sees a string as a sequence of tokens. And now basically I'm doing the same as before, creating an input field and giving a column of the 3 probabilities. Is the top 3, but in this case is all 3, but using top is just sorting them. As you can see, if I don't, I mean that with the empty string is quite a sensible result. It says that is equal probability for each topic. But for example, if I start typing, they say photons, for example, this is 90% physics. But if I say cell is 99% biology, and let's say derivative, this is 88% mathematics. So as you can see, like it's kind of quite fast to create your own things. And yeah, I mean, this is a pretty crude training. You can refine it. You can get more pages. You can get books if you add them in digital format, or you can add more topics. But it's just kind of to give you the idea. What's the difference between machine learning in Wolfram Language and Python? Well, you might ask, what are the differences between Python and the Wolfram Language? Because I think it kind of the answer to this is that what we're trying to offer here is a kind of an integrated system where you, like for example, to build this, there's quite a bit of domains, like there's string processing, there's API interaction, and there's interface building, and of course machine learning. So like one big point is that there's a big integrated system. In terms of machine learning specifically, we are trying to offer a lot of automation so that you can kind of get results immediately and then refine it, but you don't need to be an expert in the field to start using it. Okay, so we had an example with text. Let's see an example with images. So I'm using another API here, web image search, and I'm asking only for thumbnails to be kind of use small images. You don't need very big images, and I'm asking 30 of them for each class. And this thing, I don't know if you're familiar with this syntax, this is a map function. Okay, sorry, this is a map infix, so it's a shorthand for like this function here has been mapped over this list. So this value is being filled by jellyfish, blackberry, octopus, and blueberry. I should have run this code while I was speaking, probably, because this will take a bit to kind of run the search to download the images. Okay, so he's getting it for the first class, second class. So while this runs, we can have a look at what we are going to do. So we are going to basically just to have a look at what we have here. Oh, I actually had saved this before. It's okay for live presentations. You should always do this: save the internet calls and import the data. So what we're doing here is we are like these are 3 lists. We are flattening them in a long list and kind of shuffling it a bit. So they are not ordered anymore. And we are first looking at these images in a feature space. So feature space plot is using machine learning to extract features from the images and then compress them to 2D, trying to compress basically information content in a 2D vector. And okay, we see here that feature extraction, dimensionality reduction, this is completely unsupervised, yeah. And you can see that this did a pretty good job separating blueberries from octopuses. And here we have, oh, this is interesting. You see, we had jellyfish, octopus, blueberry, blackberry. So blackberry is also a phone. Given that the feature extractor for natural images is a neural network, it was able to to tell apart the phones from actually the berries, while all the berries got clustered together here. So this is the beauty of unsupervised learning. If I want to train in a supervised way, though, I can build a data set. Let me show you here what this is. So you say image jellyfish is the first one, image blackberry. So this is going to be a bit mixed, but yeah, this is kind of a lesson number 3, I guess, to check the data. So here I'm going to do something a bit more data manipulation. I'm again remixing everything, but now in the rule format. So I kept the structure to associate images to their class. Now I'm remixing it, and I'm taking, so I have 90 examples. I'm taking 80 of them for my training, and I'm leaving 10 of them to test. So I want to have some images that the classifier has never seen while it was trained, to see what, basically check what's going on. So we run the training here, and wait a second, it's processing the images, extracting the features. Now it's trying different methods. So this again, I can even show you if you do something like information on C, you get out, okay. Okay, so this was quite small. Oh no, sorry, here. You see this tried a lot of methods, naive Bayes, logistic regression with different parameters. I guess logistic regression was performing particularly well, so it tried with many parameters and it picked the best one at the end. So you see this is L1, L2 regularization and specific optimization. But this is what I meant when I say that you don't need to know this immediately. You can start just by calling classify. So let's take one image from the test set and let's use a classifier. Okay, so in this case, it learned correctly that this was a jellyfish. So this image was in the test set, so it was never seen by this classify call. We offer kind of convenience functions to be able to do this kind of advanced testing a bit more automatically. So you can use a classifier measurements functions. You pass your classifier, and then you pass the test set. And this is basically creating an object that you can then query. So you have like 58 properties. So we can ask for the report. And this is basically saying, yes, this was a logistic regression. Now the accuracy on the test set in this case is 97%. This is the baseline. Like if I guess using the probability that I see in the training set, I saw 20% of the example was blueberry, so I'm just going to say blueberry 20% of the times. So this is kind of a baseline. I need at least to be able to do better than that. And then you have this thing which is very useful is the confusion matrix. So this is basically saying like these rows are the actual labels of the images, and these are the predicted labels. So you see a perfect classifier is going to be diagonal. In this case, I only had one error, so a jellyfish image was classified as a blueberry, but not too bad here. And we can also check what are the worst classifier examples. So this thing here was classified as blueberry. Oh, okay, I can maybe see why. And this thing, I don't know, but yeah, we can check the. Okay, no, sorry, it was only one error. So yeah, this was already this. I guess this was the least probable jellyfish, but still a jellyfish, as you can see here. So yeah, I mean this. If you add more images of, for example, purple jellyfishes, then maybe this one can be corrected. But with 30 images, I think, this is a pretty good result for this kind of quick and dirty classification. Okay, let's see another example. Data prediction. So what is data prediction? We use now a predict function. We don't use classes anymore, and we use a built-in dataset, this Boston Homes. So basically this predicts the median value, even a bunch of statistics like the criminal rate, if it borders the river, quality of the air, I think this age of residence, but there's a description of all these features, what they are. So this thing is in dataset format, so we can use a nice short syntax. We still do the random sample and take a drop. So let's see what is the length of this. Why did I pick 400? Okay, so this is 506. So I picked 400 for training and left 100. So roughly 20% for testing. So I'm using this nice short syntax here. I'm putting the whole data set in here and say just predict this dataset column, the median value. So if I run it, well, maybe if I run this before, it's going to be easier. Okay. So in this case, it says input type is mixed. I have a bunch of numerical text features, and it's using linear regression. And we can use predictor measurements, which is a mirror of classifier measurements. And we say we use this predictor, and we use our test set with the same classification. And let's check, for example, a comparison plot. So given the features, I'm comparing what is the predicted value on the test features against the actual values. So again, here the perfect classifier is this line bisecting the sector. So we see that, for example, for actual values that were pretty high, we kind of undershoot a bit, but overall, like the bulk of it was on the prediction line. Oh yeah, this was doing things before. You can ask for properties beside the. So okay, let me put here. So if I do this test set 1, you see this gives a value. So I can use evaluate in place to see what it is. So if I put this, I get this value. So this is ignoring, of course, this key. It's just using these because it knows from the training that has to ignore this. So you see this is saying 17.1. It was actually 19. And one nice thing that you can ask, there are Shapley values. This is a nice property that tells you basically how much is a concept from game theory and tells you how much each of a variable had the saying in predicting the final value. So if I do a bar chart of this, we say that, for example, like these variable are kind of bringing the value down, while these variable are bringing the value up in the predicted for this specific example, of course. So this is kind of trying to do a peek into the model and asking what happens if I tune a bit one variable in this big nonlinear thing. Can we check what happens? And this is doing a lot of running of the model under the hood and try to tell you basically how it reacts to specific values. This is very useful to kind of analyze stuff like model biases, like for example, let's say that maybe this project is for a city administration trying to give subsidies or something like that. Are the subsidies being given fairly? So what variables are we analyzing? It's kind of important to be able to track these things in the model. Okay, so we saw supervised learning. Unsupervised learning is a big thing. Is difficult. Like is always a pain to benchmark because there's. I mean, if I show you a list of points in 2D and I ask you to kind of draw groups around them, two people will almost always have two different answers, especially if they're not like clearly apart. But it's also very interesting because a lot of data in the wild, I mean, you can maybe easily acquire with sensors by just collecting clicks on your website, but there's no label. You just have data. So being able to do something useful with those data, it's quite an important task. So one basic unsupervised technique is clustering. So the idea is, for example, here I show you this list of points, and I ask you like find the point clusters. Again, this has some automation going on inside. It's trying different methods and it's giving you this answer. So in this case, it's splitting negative numbers and positive numbers. But as you can see here, the answer of clustering really depends on how you set the problem, because I could easily clusterize even numbers and odd numbers. So in this case, most techniques are distance-based, so these things are closer among each other, and these are closer among each other than they are between the two groups. But again, like it's never an exact science, because it really depends on how you formulate the problem. We have several functions. Find cluster is gonna directly split the data into clusters, and you can say, for example, I don't know, like give me 3 clusters, for example, and this will try to do the best splitting in 3. Okay, it doesn't make much sense in here. It's also an art, but you say like without the number of clusters, it will try to find out what's the best split. Clustering components is also useful. It basically, instead of giving you a list of clusters, it will keep the order of the examples and give you the cluster number. So cluster number for these is 1. Cluster number for these is 2. So these numbers are meaningless. You could have replace 1 with 2 or call them A and B. The important thing is that they have the same label. You can use this function also on images. For example, here I'm asking for 5 color cluster in this grayscale space. So imagine the grayscale space is like these. You have like individual values. And so, for example, black, you see, is going. I'm using, okay, this is giving a matrix like this in 2D, and I'm using the colorize function to give false colors to it to be able to see it. So you can see like these bright spots are like orange, this kind of whitish green is black on the background. So this thing kind of gather all the pixels in different color classes. And of course, similar to predict and classify, you can use the cluster classify function, which will output a classifier function. So why classifier function? Because I mean, from what you see here, clustering, once you decided which kind of into which cluster you put every point, it becomes a lot like classification. So now you can package basically the result of a clustering in a classifier function that will use clustering methods inside to basically apply it to new points. And so, for example, this one was sending these two to one cluster and these to another cluster. So if I give you different points like minus 10.3 and 4, it will send them to the same cluster as before. Okay, so let's see immediately an application. So see, in this case, these two, when I say before, like it's going to be very difficult to divide these in clusters, but unless somebody wants to do the fancy thing and then like draw a line, like a diagonal, and say points above the diagonal and below the diagonal, I think that most people here would probably say that this is a cluster and this is another cluster, and find clusters agrees. It finds cluster of point in this case. Okay, so point classification, but of course you can do classification, clusterization of other things. We've seen some classification with images before. Let's try to do clustering on images. So here I have a list of images of physicists, because I'm a physicist. So I'm using the reliable person classifier, and I'm extracting the probabilities. So basically, this is a way, like among countless others, to take an image and get out a vector of numbers. And then I'm defining a function, the KL divergence, to measure basically the quote-unquote distance between these probability vectors. So if once I have this defined, I can apply it to all the images and create a distance matrix. And you see that, for example, the images of Marcury in the probability space, they are kind of quite close to each other. And Feynman images as well. Einstein images not so much, maybe because I don't know, this is slightly turned. I'm not sure. Maybe this has less padding. That can be all variety of regions. The thing is, now that I have this, I can say find clusters using these probability vectors. So the fine cluster will do something similar to this internally. We'll build a distance matrix between the examples and try to find the one that are close. So I say fine clusters of the probabilities. So this arrow now is not label data. I mean, it is a label, but it's not classification. This is just saying, instead of returning the vector, tell me this thing. It's kind of a marker. Tell me this thing. So I can show you without. So if I do this, this is clustering. You see these probability vectors. It's clustering them together, but it's not so informative. So I say, okay, now go back and replace each probability vector with the phase I extracted it from. And you see that, for example, this thing clustered together correctly these images and 2 images of Feynman, but it wasn't super sure. So like this older Feynman was put together with Einstein. Of course, you can refine it if you have like kind of maybe more images. It will find better cluster boundaries. But again, this is not training supervised stuff. Yeah, it's just trying to find similarities. So another way to improve this would be to have a better feature extractor. So here I'm kind of piggybacking the notable person classifier and taking probabilities out. But I mean, we can try. We can do, for example, feature space plot on faces, which is something I did before. And okay, these are all a bit close. So okay, no, let's say the network that is extracting. So this is interesting. See, the network that is extracting information from images before crashing them to 2D was trained on like kind of objects, animals, plants, not humans specifically. So it's kind of picking up a lot more on the difference in background than the difference in what people actually are. While the notable person classifier was trained on people, so using these probabilities as features to build the clustering is actually more informative. No, these images are just coming from. I think I dragged them from an image search in a browser. But you can use web image search as same as before to build your own. Okay, so and another thing that you can do, another like input type I think I've never shown, is colors. So for example, we can build kind of a dominant color function that tries to find what are the main colors in an image, which is also clustering. So here I come from image processing. So here I'm again start with color conversion, and so this image is in RGB colors, red, green, and blue, but there are other color spaces. So the LAB space is well, I don't want to go into color theory, but it's a space where like kind of distances kind of mean something for a human in a sense, a bit more than RGB. So given that I'm trying to cluster pixels, I want to do this in a space which is perceptually more accurate. Then as I said, I need to go to a vector space. So in this case, I'm just going to do the dumb thing and take the image data and flatten it. So basically, if I now do random sample of image data, let's take 10 samples. I have, you see, 10 pixels. These are LAB colors, so this is how bright the color is. And these two are kind of their color opponencies. One is a magenta green axis and one is a blue yellow axis. Okay, anyway, now that I have this pixel, I say, okay, for example, try to find, using the method key midweights, we're going to see what this is later, find 5 clusters on all these pixels. So this is giving me the functions, and I can reapply it on the image data to classify it. So now I kind of have a bit of code machinery. I use the function pick to basically, now this is a list. This is a list of pixels. This is a list of decision, 1, 2, 3, 4, 5 for each pixel. The function pick is a kind of where in Python. So I have a list of pixels, a list of decision, and I say, okay, pick all the pixels with decision 1. This is a range 5, yeah. So 1, 2, 3, 4, 5. So this is basically, this code here is splitting my pixels in 5 different groups. Then I'm using this to map. I'm mapping mean along all these 5 different groups. So I can actually show you this separately. So like these are my 5 colors, and these are LAB color. So I can take this and I can do LAB color. At means change the head. So instead of a list around this, I want LAB color. So I want to basically convert it to this. And now this is, okay, this is going to be kind of the sky, I assume. So now if I do this, these are the main colors in the image that were identified with this clustering technique. And now I can use, for example, if I want to see what these are on the images, I can use some image functions to basically take out the areas that correspond to these. So, for example, now this image data was completely classified, in one of the 5 clusters. So I can repartition it. So this is making same as before. This is I can use colorize. So these are where these 5 clusters are in the image. So this is a matrix of 1, 2, 3, 4, 5, and I'm using it in the component measurement functions together with the image. So this is my image, and this is my it's called label metrics in image processing, and I'm taking the mask out. Why? Because now this way I have a list of binary masks, and now that I had this, I can take my list of colors and I can use the function image multiply. So this is threading, so that means that every mask is multiplied by the color, and then I'm adding them all together. So basically, this is a quantized version of the original image that I build by clustering colors. And I can say, I think this calls IMG. What would they call it up there? I call it, oh, I didn't call it, no, image. Okay. So this is the original image, and this is a quantized image. You see, it doesn't have many colors, only 5. So, for example, it decided to pick green to do the darker pixels here between the not as sky pixel, but not really yellow. So this one, limitation of only picking 5 of them. But overall, it's still pretty not completely accurate. Like I think there's the stem here that's not present. Is it stem? I don't know the flower parts in English very well, but most of the content of the image was recovered. So like here I have a completely independent application of machine learning clustering, in this case to build a color reducer for an image.